When we talk about the universe, we're talking about everything: Earth, the Sun, the solar system, the Milky Way galaxy, all the other galaxies, and everything else we haven't even seen yet. In fact, it even includes things we can't see because the light from them hasn't had enough time to reach us yet. It even includes things we'll never see, no matter how long we wait, because the universe is expanding faster than the light from them is traveling towards us. So, it will just never reach us. That leaves us with a pretty major chasm in our understanding of the universe. In an attempt to get to the bottom of this, the James Webb Space Telescope has weighed in on this situation for the first time. But it did not solve the mystery. In fact, James Webb actually thickened it. As the premier telescope gazes into the distant past, it unveils mysteries that were previously beyond our perception. One of these surprising new discoveries even shattered our fundamental understanding about the universe and reveals that we may be completely wrong about the size of the universe. Astronomers say that we did not expect to see something like this in the Webb image. The first galaxies grew differently than we expected, and we don't know why. Their old predictions were wrong. Join us as we dig deep into how James Webb just upended our understanding of the size of the universe. Let's face it, space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. To give you some perspective, let's begin by considering local space. Assume that the distance between Earth and the Sun, known as 1 astronomical unit, is 1 centimeter, instead of its actual 93 million miles. In all of human history, we have physically traveled an imperceptibly small fraction of that 1 centimeter. You can think of a scale model solar system in your room, your neighborhood, and your town. On that scale, Jupiter would be 5 centimeters from the Sun. Keep moving off, say to the right, and imagining the relative distances. Saturn would be 10 centimeters from the Sun, Uranus 19 centimeters from the Sun, and Neptune 30 centimeters from the Sun. Little old Pluto would typically be about 40 centimeters from the Sun on this scale. However, the physical diameter of the solar system is far larger than that. The outer edge of the Oort cloud, the enormous shell of perhaps 1 trillion comets, would lie 10 football fields away. And we have thus far traveled a tiny, almost invisible fraction of that original 1 centimeter. And that's just our solar system. The nearest star, Proxima Centauri, is 4 times farther away than the outer shell of the Oort cloud. The enormous gap between even the nearest stars would be staggeringly large. The actual distance to Proxima Centauri is 4.2 light-years, meaning that light, the fastest thing there is, takes 4.2 years to travel from that star to our eyes. We can take quantum leaps upward in universal scale too. The Milky Way galaxy is one of at least 100 billion galaxies in the cosmos. The diameter of the Milky Way's bright disk, which we are in, is at least 100,000 light-years. We are a little more than 26,000 light-years out from the galaxy's center. The most distant photons from our own galaxy have been traveling to us for 1/3 of the length of human history. And a little like nesting dolls, we can follow cosmic structures out to larger and larger scales. Our local group of galaxies, as Edwin Hubble termed it back in the 1930s, contains at least 55 galaxies in a sphere spanning about 10 million light-years. Local group members include our nearby friends, the Andromeda Galaxy and the Triangulum Galaxy. Countless small groups of galaxies are even farther away, and if we travel some 55 million light-years, we get to the center of the largest cluster of galaxies in our cosmic space, the Virgo cluster. This group includes some 1,300 galaxies of all types, but larger and more massive groups of galaxies lie far more distant from us, nearly countless numbers of them. When we get up to the largest cosmic structures known, we can talk about superclusters and walls of galaxy clusters. Examples include Laniakea, which we belong to, a structure that stretches some 500 million light-years across, and there are dozens of examples of other large structures. So how big is the universe? It's around 93 billion light-years. The 93 billion years is just the observable universe, the universe which we can currently see. The observable universe is likely only one section of the universe, and beyond it, there is likely even more space filled with stars and galaxies. The reason why there is an observable universe is that the universe has not existed for an infinite amount of time. Rather, the universe began in the Big Bang some 13.8 billion years ago. A finite age for the universe means that objects beyond a certain point, called the cosmic horizon, are simply too far away for their light to have reached our eyes. Everything we can currently see in the universe is part of our cosmic bubble, called the observable universe. But what about the entire universe? How can we know about parts that are so far away that we have not even seen them yet? That's where things get interesting. By using the Bayesian model averaging, scientists estimated that the universe is at least 250 times larger than the observable universe, or at least 7 trillion light-years in diameter. The bottom line is that the visible universe is incredibly large, and the entire universe is truly enormous. Indeed, the entire universe could be infinitely large. As a result, while we can make estimates as to the size of the universe, scientists can't put a number on it. Scientists now expect we can get closer to the answer with the arrival of James Webb. Just a few days ago, the Webb telescope celebrated its second anniversary as the world's largest and most powerful space observatory. Unlike its predecessor, the Hubble Space Telescope, James Webb specializes in detecting infrared light. This allows it to peer through the cosmic dust and gas that obscure visible light, providing researchers with unprecedented views of distant galaxies, nebulae, and even exoplanets. The clarity and detail of Webb's images have stunned both scientists and the general public alike. With its remarkable resolution and sensitivity, James Webb has allowed astronomers to study the formation of stars and galaxies with unparalleled accuracy. By capturing infrared light, it has unraveled mysteries that were previously inaccessible, shedding light on the early stages of the universe's evolution. However, it took a remarkably long time for the first light emitted by a group of ancient galaxies to reach the James Webb Space Telescope. Astronomers have calculated that the photons were in transit for more than 13 billion years, almost the entire history of the cosmos, before they reached the orbiting observatory. The results are scientifically dramatic and have revealed that the universe was already deep into the process of star formation only a short time after its Big Bang birth. Although the photographs themselves are scarcely stunning in appearance, just a handful of smudges, a couple of glowing spheres, and an image described as a glowing dog bone, nevertheless, the world of astronomy has been dazzled. Among the objects caught in the telescope's giant mirror is one that turns out to be the oldest known galaxy in the universe. The prosaically named J0521 plus 1024 appears as it did a mere 320 million years after the Big Bang, long before the creation of our own planet. It also turns out to be tiny compared with our own galaxy, yet it was clearly creating new stars at a rate comparable to the Milky Way. This stellar fecundity is shared by several other ancient galaxies photographed by the James Webb Telescope. These snapshots of the infant universe show that the first stars and galaxies had already formed and were evolving much earlier than most scientists had expected. As Professor Brant Robertson, an astrophysicist at the University of California, Santa Cruz, said, "These galaxies are very, very young, yet they have already become hotbeds for star formation. It's remarkable." This enthusiasm was shared by Kevin Heinlein, an astronomer at the University of Arizona, Tucson. He said, "We have observed the earliest galaxies in the universe, and it has been thrilling. It has opened an entirely new chapter in the history of astronomy. It is telling us the universe was dynamic from the beginning." However, James Webb's breathtaking images of brilliant stars are not the only stunning results. One galaxy, an almost indiscernible smudge of light labeled Sears 93316, is causing real excitement among cosmologists and astrophysicists. It is reported to be a staggering 35 billion light-years away. At first, it may seem difficult to explain how the distance between our Milky Way and Sears 93316 has grown to 35 billion light-years, given the universe has only been expanding for 13.8 billion years. How can it be that the size of the universe is bigger than its age? Let's find out. We all know that the expansion of empty space is not constrained at all by Albert Einstein's fundamental velocity of light speed limit. However, When it comes to objects in an ever-expanding universe, the concept of distance becomes a bit murky. So, we need to take a closer look at what we really mean by distance. First, it's important to realize that we cannot measure cosmic distances directly, at least not outside our solar system. For galaxies, redshift is the only proxy we have, and in truth, it only actually tells us how long the galaxy's light has been traveling through expanding space. For instance, a galaxy at a redshift of 5, its wavelengths are 5 times their original value, means the light has been traveling for 12.6 billion years. This is called the light travel time or the look-back time, as we are seeing the galaxy as it was 12.6 billion years ago. Intuitively, you would assume that this particular galaxy is 12.6 billion light-years away, but in reality, the galaxy is much further away. After emitting the light that we received, Sears 93316 and our own Milky Way have been pushed further apart due to the expansion of space. The true distance of our redshift 5 galaxy, often called the comoving distance, is currently almost 26 billion light-years. The exact value depends partly on how the universe has been expanding through time, which we don't know in detail. But in any case, a remote galaxy is always further away than its light travel time would suggest. Surprisingly, despite being 26 billion light-years distant, Sears 93316 appears as a slightly extended object on the sky with a particular, albeit small, angular size. That's because its perceived angular size was set at the time the galaxy's light was emitted, 12.6 billion years ago. Back then, it was much closer to our Milky Way. For a redshift of 5, it emitted the light when it was 4.3 billion light-years from our galaxy. This is its angular size distance. Because the expansion of space constantly moved the goalposts back, it nevertheless took 12.6 billion years for the light to reach us. If this isn't confusing enough, there's also a luminosity distance, which tells you how faint the galaxy appears because of the expansion of space, which decreases both the energy and the arrival rate of photons. Our remote galaxy looks much fainter than you would expect for its actual comoving distance of 26 billion light-years. In a non-expanding universe, it would only be this faint if it were located at a whopping 155 billion light-years. Returning to the recently discovered galaxy, Sears 93316, the light has been traveling from this galaxy for 13.5 billion years. If you could lay down a ruler today, you'd measure its comoving distance to be around 35 billion light-years, because the universe was much smaller when the galaxy emitted its light. Its angular size distance is 2 billion light-years. Finally, the expansion of the universe decreasing its brightness means its luminosity distance is 615 billion light-years, giving it an incredibly low surface brightness. It should be obvious now why it hadn't been observed until JWST came along, and its discovery is an impressive tribute to the telescope's light-gathering power. Because of the finite speed of light, we see distant objects as they were when the light was emitted long ago, not as they are now. To many people, this may seem to be a nuisance. Astronomers will never be able to learn what remote galaxies look like right now. However, to cosmologists, it's a wonderful gift of nature. Thanks to the look-back time, they are able to study the early youth of the universe. All you need to do is look very far away into space, and you're automatically looking far back in time. Thus, the full 13.8 billion-year history of the universe becomes accessible to scientific inquiry. However, note that James Webb is an all-purpose observatory. Thus, while focusing on distant galaxies and star formation, its powerful, sharp eyes also see details in solar system objects beyond the reach of conventional telescopes. For example, Uranus appears regal, circled by glowing rings and a smattering of moons in a new image captured by James Webb. While previous images of the planet taken in visible light by NASA's Voyager 2 probe showed it as a uniformly blue orb, Webb's infrared view captures its dynamic nature. It even reveals more detail than the observatory's last image of Uranus released in April. On view in the new image are storms, rings, moons, and a gleaming polar ice cap. Uranus is unique among the planets for orbiting on its side with an axial tilt of about 98 degrees. It hosts the most extreme seasons in our solar system. When one Uranian pole is facing the sun, the other is shrouded in a cold, dark 21-year-long winter. Currently, the planet is approaching a solstice in 2028. The polar cap shown on the right side of Uranus in Webb's photo will face the sun head-on. Astronomers will watch to see what knowledge they can gain from this prime view of the pole. The brilliant image captures the elusive Zeta ring, the innermost diffuse ring around the planet. Observing the rings could inform future missions to Uranus. As NASA wrote on social media, humans want to send a spacecraft to visit Uranus up close. It's necessary to understand how to navigate debris from its rings. 9 of Uranus's 27 moons can be seen surrounding the planet in the new image, shining like pearls. Individual astronomers discovered the ice giants.